Hi, this is Haiyi Wang. Today I would like to introduce my thesis project, Material Capture and Generative Rendering with Phenomenological Reflectance Models. Replicating realistic objects on the screen has been a challenging task. It is a very broad task as there are many factors such as scene illumination and surface roughness are affecting an object's visual appearance. In recent years, two typical solutions would be used for realistic image synthesis is graphics rendering and neural rendering. Graphics rendering is a process of transforming 3D assets into realistic images, while neural rendering introduces machine learning methods into traditional rendering pipeline to generate astonishing results with good quality. I first formed the idea of my thesis in actual development. I was working on a graphics rendering pipeline and designing rendering algorithms. I noticed that major time was spent on asset preparation and rendering preview creation. Sometimes the algorithms are already implemented, but still developers need to wait for artists to create suitable assets for further evaluation in the rendering engine. In the meantime, the lack of rendering preview causes that developers are usually working without a clear idea of how the visual effect should finally look like on the screen. So they are working with a rough and ambiguous description, which often causes additional communication costs and development delay. I started my survey and found that advances in the field of neural rendering and material capture could assist us to design a novel rendering pipeline that enable us to quickly capture material and create rendering preview. Two work was mentioned here was Deshawn's work in 2080, which utilized an encoder and decoder unit architecture to capture BRDF decompositions from single image. The other one is John's work in 2023, who introduced an additional hypernetwork to a diffusion model to enable strong control over the same parameter while generating high quality results. We form our research goals after analyzing both the advantages and disadvantages of traditional rendering methods and neural rendering methods. We noticed that while traditional rendering techniques have full control of the scene parameters, it usually requires a lot of manually created assets and take long rendering time. While generative rendering techniques have full automatic inferencing ability, it requires lots of training data and has no fine-grained control over the scene. Thus, our goals are to provide quickly asset acquisition and rendering preview creation while maintaining fine-grained control of the scene parameters. Ideally, the training process shouldn't require too much training data. We start with choosing a suitable scene representation in our research. Our choice includes continuous representation such as field function in nerve or point cloud, or discrete representation such as point cloud and the voxel grid. We finally choose the per pixel maps as our scene representation, given its compatibility with traditional rendering engine and the ability to provide users with strong control over the scene, since users could directly edit the pixel values to change the scene parameter. In terms of reflectance model, we choose among different reflectance models, such as measure data and heuristic-based models. We finally take phenomenological model as our solutions, given its popularity in both enterprise development and academic fields. It is worth noticing here that although two different phenomenological model, metallic model and specular model, are equally important in the field of graphics development, I would say that the metallic model is not getting enough attention in previous researches. Most most researches in the field of computer graphics and neural rendering are based on specular model instead of metallic model. These two models are equal in terms of restoring a certain given scene. In terms of network architecture, we follow the network created by Deschamps and added it to allow the original network to adapt to the new task. The original network is designed for the specular model, thus it outputs four maps, which is surface normal map, orbital color map, specular color map, and the surface reference map. We added the output layer to fine-tune this network, so the new network now output 6 maps, which are color map, surface normal map, metallic map, roughness map, specular level, and the ambient occlusion map. So first we replace the original 3-channel specular color map with a new 1-channel metallic map. Additionally, we introduce 2 more physical parameters, which are specular level and ambient occlusion. We hope that the adjusted network could learn these 2 parameters, which are often used by many artists. In the design, in terms of the design of the rendering network architecture, we follow the paradigm set by John in his papers about control net. So we connected an additional network to original stable diffusion network. And we copied the parameters from stable diffusion into our control net and fine-tune this control net on our created dataset. The control net takes a reference map as input and output results of given objects. Here is an overview of the rendering pipeline. The rendering pipeline takes a single image as input and provide BRDF decompositions as output. The results in the middle could be directly sent into any enterprise rendering pipeline to create rendering results. Alternatively, if the rendering algorithms are not yet implemented, we can send the results into the control net, which is the rendering network, to create preview. The preview can be used as reference in the actual development. In terms of evaluation, we run several comparisons in terms of qualitative, quantitative, and ablation study. When comparing the quality of the result, we compare ground truth with capture results. We also compare input images with re-rendering result of capture solutions. We run the comparison on both synthetic data and real data to prove the generalization ability of our network. In terms of quality comparison, we calculate multiple metrics such as root square mean error to evaluate the quality of the re-rendering results. In Ablation Study, we ablate the use of control and prompt separately to better understand the contribution of each component. We set up our environment by preparing the necessary data and the hardware. We create 2 synthetic datasets in specular model and metallic model separately. We choose 7 classes of representative material in real world. They are leather, tiles, fabric, stone, etc. The dataset is with good scale and good representativity. In terms of hardware, we prepare 3080 GPU and A100 GPU for training the capture network and tuning the control net. Here are some results of material capture. We input some photos captured with cell phone under its built-in flashlight. And below you can see the reconstruction results of Deschamps' work and our work. While our work preserve good quality of the input images, we have better glossy results compared to Deschamps' work. And here are some comparison solution capture solution comparison on real photos. We can see that our work has better performance, especially in this highlight area. Our method have shown its robustness towards the interference of strong lighting area. And here are some results on synthetic data. We can see here are the comparison of the re-rendering results, and here are some matrix of Deschamps' work and ours. While our work has better appearances, especially in glossy area with strong highlight, the matrix shows that our work has similar performance, which means we generated images with similar quality compared to Deschamps' work. And at last, these are some captured solutions comparison of synthetic data. We can get similar conclusion here is that in this area with strong highlight, the original network tend to understand that there is a specific distribution among this highlight area in the diffuse map and roughness map, while our work tend to decompose the material from the light and get a more realistic results. And here are some results of the neural rendering. We can see the comparison between different images generated with different input condition. The images on the above are accepting high roughness map as the input condition, while the images on the bottom are using low roughness map as input condition. We can see clearly that the lighting is more compact and dense in when the material is with less roughness. This comparison has proven the rendering network's ability to generate results of certain objects while controlling its surface roughness. And here are some results of ablation study. We ablate the control in this comparison. We can see that if we remove the roughness control, the output is still realistic, but the visual result was immediately different by removing the control of surface roughness. We can see that after applying this roughness map with low roughness onto the brick is more is formed with more regular shape and present similar pattern like the input roughness map. Similarly, after applying a low roughness map onto the diffusion model, we can see that the output result is more smooth and less rough. Here are some results of prompt ablation study. We can see that after ablating the roughness map, after ablating the prompts, the output results are a gray surface with typical roughness features, but you cannot tell what kind of material it is. However, after applying the prompt, such as brick tiles and brown leathers, into the control net, we can form results with typical features of certain materials. Notice that even if we remove the prompt here in the ablation study, we can still see the ability of ControlNet to enforcing the result with given roughness features. So here are some interpretations of the results. We can see that the result shows that we successfully applied a network compatible with the specular model to a new but similar phenomenological reflectance model, which is the metallic model. We also explored that how to use learning-based method on 3D asset to create rendering preview. We met several limitations during our study. The first one is that although we built a novel dataset that covers typical materials and support both specular and metallic models, we have limited access to more diverse and high-quality assets. Second, we have limited computing resources. First, we use approximated rendering function, which can be optimized further in later research. If we have greater computing resources, we can use more realistic physical models of rendering functions to generate more realistic results. At last, we met this ill-posed problem that is the visual appearance is decided by both scene illumination and the surface properties of the given material. This problem could be alleviated by redesigning the rendering loss function and provide better performance. To conclude, this study proposed a rendering pipeline to address the tasks of rendering, material capture, and rendering preview creation. We provide these functions automatically while maintaining the adaptability towards the final scene. First, we create two datasets with phenomenological reflectance models, which are constructed using open source assets. Secondly, we fine-tune a material capture network compatible with the specular reflectance model to adapt to the metallic reflectance model. Finally, we trained a ControlNet model to provide generative rendering result using reflectance model parameters as control conditions.